So it's about finite discrete probability distribution. So I'm feeling a bit embarrassed with the previous talk because we have learned that everything is continuous in this world. So, okay, if you think that probability is only continuous, you can leave the room, no problem. But actually, more seriously, I think that even if the reality is continuous, if you throw a dice, it's a continuous phenomenon, but you are interested by a specific view on the world. So what it is about Lea. So it's really the cornerstone. It's really working with finite discrete probability distributions, and also some probabilistic programming. So I will show in this presentation what I mean by that. I'm really happy that Peter has defined what is probabilistic programming, because it was a bit difficult for me. And it's, of course, in Python. So is it, again, another stats package? So I think the answer is no. So because it's only discrete. So what's a bit special also is that it is supposed to support any Python objects. I say almost because the requirement is that it should be hashable. Something not common also is that the probability are not modeled as floating point number. These are just integer weights. So I will explain maybe later what's the interest of doing that. Also, I will introduce some concept about calculus and probability distribution. Maybe the most important point of Lea is ease of use. So, okay, it's maybe a matter of taste, what is easy or not. But that's something I kept always in mind. Okay, try to give the user a view which is understandable about the probability model. Okay, so I would like first to make a short introduction about a session with Lea. I will model here a coin flipping with head and tail. So if you do that, Lea from Val's head and tail, it will associate the probability of 1/2 for each of these events. Very simple. If I put in from Val's several values which are duplicated, actually it will count the frequency of this value, and it will again produce a probability distribution, but this time it will be 1/3, 2/3. Okay, maybe you are not very used to have this fraction. Maybe you can see that it's a bit childish. So there are several other formatting views you can ask to display this probability as floating numbers. No, you can actually do the same biased coins definition by putting the probability weight or the frequency, if you prefer, like this, like a sequence of tuples with value and probability. So here, bias flip 2 is exactly the same as the previous definition. Okay, let's continue. I repeat here the definition. What you can do on a probability distribution is to take a random sample. Here, I just take 10 because it fits on the slides. You can maybe see that's more or less you have more tails than heads, but it's not, since it's probability, we are not sure. If you want to have better confidence in the tool, you can here take a sample of 3 million values in this distribution. And if you want to check what is the frequency of each value in this sample, but it's very simple. With all I've shown before, You simply put from vals and you put an asterisk, a star before sample, and it will expand the 3 million values as arguments of from vals. And the result, it's here. And okay, maybe it's not very clear, but if you do as float, you see that, as you could expect, the frequency is more or less close to the probability. And as you can expect, the larger the sample, the more accurate your sample will be. Okay, let's continue with a die now. There is another method interval which defines discrete value from one value to another. You can take the mean, you can take the entropy. Entropy means it's a concept of information theory. It gives a value that estimates how random is your variable, so it could be interesting in some situation. Okay, let's continue with something maybe more interesting. I have this variable die x, which is represented die. I can do some expression, arithmetic expression on it. For example, here, I subtract the mean and I multiply by 2, and this is the result. So you see, you can make very concise expression and produce new distributions. Here, for example, I take the modulo 2, and okay, and we can see, as you expect, that there are as many odd values than even values when you throw a die. You can do also something more involved, like calling a function on each value of the die, like here. What it means is that I'm applying a function, a lambda function. Whenever the value is even, I will display even, and sorry, I will return the string even. When it's odd, I will return the value odd. And if you do that, again, you have a new distribution. So Lea is always taking some distribution, produce new probability distribution. So globally, I spoke about calculus. What I mean by that is that in classical programming, you have a function f which is purely deterministic, with, in this case, 2 inputs. It produces 1 output. What's interesting here is that suppose that we are uncertain about the value of A, but we have some probability distribution. We are also uncertain about B, but okay, there are some values with probability. Then here the system will be able to calculate for each value behind the scene all the results and produce a new distribution. So it's a common pattern that you will see everywhere in the other example. What's interesting here is that not only you can produce outputs from inputs, but we will see in other example that considering some values in output or some condition you put in output, we can infer what are the value in inputs. That's really, I think, something characteristic from probabilistic programming. Is you produce relationship and then there is no real input output. It depends of the evidence that you have. Okay, so far. Okay, I will. So here I'm trying to show you how you can easily produce a new variable dice, which is the addition of 2 dice that you are throwing, which are independent. And you see that it produces, as you can expect, probably most of you knows that okay, the resulting distribution is not uniform. So what else can we do is doing stuff like this, putting comparison. I would like to know what are the probability that my dice is less or equal to 3. So you simply put this formula and it will calculate a new function. If you want to extract the value of true, you have to do to use the method P with the value which are interesting for you. Okay. Okay, here it's the conversion floating number. So here it's maybe another interesting case. I don't know if you know a game called craps. A craps, by definition, is when the two dice give a result 1 or 2 or 12. And here, just for the demonstration, I show you how you can represent that in Lea. You simply say, okay, either dice is less or equal to 3 or it's 12. And you get, again, the probability 1/9. Okay, and the last one is, okay, what's the probability not to have a craps? Here the expression I put is that the dice value is between 4 and 11 inclusive, and no surprise, it's 8/9. Okay, so maybe something strange, I don't know if you have heard about non-transitive dice. So imagine that you have 3 dice, but not usual dice. Each die has special value defined like this. So some numbers are repeated twice. So imagine that you want to know which die beats other die and which probability. So if I do this expression, I will get here this result. That means that on the average, there are 5/9 chances that die A, a throw of die A is greater than die B. So die A is stronger than die B. Then I do die B, I compare die B and die C, and again, I see that die B is better than die C. So you could say no, it means that in any case, die B will beat die A, sorry. If you check, what is funny is that it's not true. Die C beats die A, so it forms a kind of cycle like this. So previous presentation, I showed that, and someone in the assistance says, it's not true. And but it's true. You can see on the internet that there is a complete theory about non-transitive dice. Okay, now before getting further, I would like to introduce something. It's rather a contrived example, but it's very, very important to understand that. Suppose, again, I define my sum of 2 dice. What will happen if I do dice minus die x? Actually, what happened is this. You get back the die y. What it means, it's very important, is that there is a kind of lazy evaluation. So dice is not only a calculation over all the possibilities. It's dice remember the fact that it was built from the 2 other dice. And I can continue this example. If I subtract again die y, I got this expression. It means that, okay, I have the result of my 2 dice, but I subtract 1 die after the other, and then I'm sure I will get 0. So it's important to understand that all these variables are dependent with each other, and the system keeps this relationship together. It allows us to do conditional probabilities. For example, Here I want to know the distribution of dice value, knowing that the dice is less or equal to 4. So for that there is a method given like this, and it gives you the probability of each value. It produces a new probability function given new evidence you have. I can do other example. Here I'm using an input variable, die_x. I know something about it, and I ask what will be the result of the two dice, given that the first die is less than or equal to 2. Again, it gives something. And finally, I can even take the dice variable, let's say the outputs, and given evidence on this output, I can infer what the probability of one of these die. And in this case, if you have understood this, the result is true. It's certainly true, because if the result of the sum of two dice is less than 3, each of the dice should be less or equal to 2. So it's something obvious. So what I've shown here is that you can equally go from causes to effects, or from effect to causes. So now I would like to go a bit further. Yes? Okay, I can bring it back. Yeah.
I presume it handles adding a dice to a coin.
Coin flip, yeah. Sorry, I don't understand.
Yeah. To add dice to a coin flip.
Yeah.
It handles that as well, it just gives you 12.
Yeah, exactly. Yeah. You can combine everything together. Here, of course, then you have to associate a number to coin flip. Head will be 0, tail will be 1, and then you can add. So yeah, everything is possible, provided that the values of the distribution are that you can combine them together. You can do whatever you want. So now we have seen this given function, which allows us to do conditional probability. If I add some new function like CPT, conditional probability table, I can do Bayesian networks and reasoning. So for that, I would like to present a murder case. So imagine Dr. Black has been murdered last night. It's fictional, so... And, okay, we have 3 suspects. Maybe you know this character, you have seen them: Mrs. White, Mrs. Peacock, Colonel Mustard. And we know that there is only one is the killer. So imagine we have prior probabilities like this. For some reason, you know that Colonel Mustard has more chance to be the killer. Okay, how do you model that in Lea? We have seen that, very simple. You can do associate prior probabilities with the user. So imagine now we have new information. It's a bit more complex now. We say if Mrs. White is the killer, then she'll be absent the next day with a probability of 90%. Otherwise, she'll be absent with probability 20%. How do you model that? It's like this. You put Lea if. There is an underscore because otherwise Python is not happy because if is a keyword. So if underscore, and you put the condition using the variable killer that we have defined, and you put 2 probability, 90% and 20% is the way you do that. Okay, now new information. Mrs. Peacock if Mrs. Peacock is innocent, she knows who is the killer with probability 75%. So again, here I use the not equal to, because if she's innocent, the killer is not Mrs. Peacock. And there is a trick here, because if if she's the killer, we could expect that she knows who's the killer because it's herself, unless she's completely paranoid. Or so again, I can elaborate. Here it's to show there is another rule. We can combine condition with or and associate probability. Now, what is important now, we have new evidence in the system. Mrs. Peacock is absent. So how do you model that? I create a variable evidences because there will be other, and then I put killer given evidences, and we see here that the prior probabilities are changed from the prior one. Initially, it was this. We see that it changed a bit, not that much, because the fact that Mrs. Peacock is absent is not give not such much information as we need. Imagine now that Mrs. White is present, so I define it as not because I define a variable Mrs. White is absent, so Mrs. White is present is the negation of that, and I add this in my evidence by using &equal, which is a Python statement. Here we see that again the change that Mrs. Peacock is the killer has changed a bit. Now imagine that we have heard that we heard Mrs. Dr. Black telling before he has been murdered, she killed me. So we know that the killer is a woman. So it's a new fact. And to model that, I built a new distribution, killer is woman, by using slicing. Because if the name begins with Mrs., I know it's a woman. Again, I put in the evidence. And here, okay, we know it has removed Colonel Mustard, which is innocent because he's a man. And we know that there is a great chance that Mrs. Peacock is the culprit. Is it 1 minute? Okay. Okay, so what I've been done here is building a Bayesian network, and we have seen that by putting all these rules in a very declarative way, we were able to to take evidence one after the other and infer who is the killer. So, okay, I think I will stop here. But there are many things that I can show you also about Lea. Maybe I can just, I will drop that. Yeah, sorry. Yeah, it just, okay, an example with cards. Just on a lighter tone, what I've made some years ago is a bullshit generator. So it's basically a Python program which defines words, verbs, and which defines a grammar also. But Lea is interesting here because I put several probability to use the grammar rules. So the most complex rule in the grammar are less likely to be used. And then I can show you here, okay, a small sample of what it does. Yeah, okay, so that's not maybe, it's really bullshit, so. Okay, these are information about the project. If you want to know more, there is a complete tutorial about that. Okay, thank you very much for your attention.
Do we have any questions?
So if you can speak not too fast, because as you know, I'm not English native.
I was just wondering, would this be used much in industry? Do you know?
Is it used in industry? No, no, not as I know, no. But it's something like still in exploration phase, so I experiment things. I think that there are interesting concepts that are not in other like PyMC, so it's not compete with PyMC or other tools, but okay, I've received some feedback from a searcher in Singapore who's trying to do machine learning on statistics, and okay, the results so far I received some positive feedback, so okay. But I would be happy. So if you have any comments, either positive or negative, it's very, you are really welcome to send me an email because okay.
Is it used much in Dungeons and Dragons? Because that seems very
yeah,
useful.
good point. If you go on this on the tutorial, there is an example page, and I have a full RPG example, and it's really very suited for that because you can have a distribution of your attack value compared to the defensor and the damage stuff, and yeah, you have really nice results if you play Dungeons and Dragons. Yes.
Any other questions there? Going once, going twice. Thank you very much, Pierre.